So I'm going to talk about joint work with Hugo Winter, a PhD student who's just started at EDF, and Simon Brown, who was asking one of the interrogating questions earlier on. And we're trying to develop some extreme value methods to apply across a broad set of heatwave type of scenario questions. So just to be clear what I mean by a heatwave, it's a set of hot days. This is something we don't see very often in Lancaster, I should stress. Set of hot days with increased mortality. Okay. So the mortality comes from basically heat exhaustion, where the body temperature starts to exceed sort of critical levels of about 35 to 37 degrees. Now, the impact of a heat wave doesn't just depend on it being one particular hot day, but to have a series of hot days is obviously worse because the human body gradually weakens through that period. And obviously the total effect on the heat wave is felt through its spatial impact as well. So both space and time are very key to determining the characteristics of heat wave. Now that critical level when the body starts to be affected by temperatures varies a little bit from place to place. Around Europe it's to 35 degrees in a number of places been found to start to have where more mortality is affected, and with sort of increased mortality going up by 20 to 50%. So what we're going to be interested in here is looking at extreme levels where not just the individual extremes important, but the clustering of extremes in space and time are key to determining sort of the risks to humans from these heatwave events. So that suggests we need to worry about the dependence structure that's creating these heat waves, and in particular also covariate factors which might be, explain some of that clustering away. So I'm going to look at two case studies through the talk. First of which is the European heat wave of 2003. This led to massive numbers of deaths, 4,000 deaths, and huge loss to agriculture. The data I'm going to look at is from a site in France. We've got about 70 years of data, and if you look at that data, 35 degrees is basically the 1 year level. So this critical level is exceeded on average once in every year at this site. Now in this 2003 event, basically it was nearly 40 degrees was the maximum temperature, and there were two type of events in a couple of weeks period where this happened. There was where this event occurred. There was a 2-day period where they had these very extreme levels, which maybe isn't so rare, but there was also an 11-day period where each consecutive day in the 11 days it exceeded the 1 year level, and that was the event that caused the lots of problems. So we're looking at a heat wave event in this terms. We've got some high critical level. We're interested in obviously somewhat the peak level above that, but that's not the vital measure of the extreme here. Possibly more important is the duration of the event, how long it's above this critical level, or maybe some aggregate of the effect of the height of the values above the threshold and the time in measures certain forms of severity. The critical thing is we need to understand and be able to sort of look at the stochastic properties of a heat wave during periods of exceedances of high thresholds. In the second case study I'm going to look at, it's to do with a heat wave in South Australia in 2009. So this heat wave was pretty severe over the whole of southeastern Australia. Fewer deaths, but a lot of people treated for heat-related illness. This was, in particular, Melbourne, so that's down here. This was Melbourne's record temperature. Temperature we often see in Lancaster again of 46 degrees. Adelaide, it was their third highest temperature, so that's over here, if I can point a bit more steadily. And so this was quite a severe event over a big area of Australia. This is the map of the event itself, and you can see a sort of structure to the hot temperatures here sort of coming inland, but obviously some of those in the desert areas, they often get very hot temperatures, so maybe that isn't so extreme there, but in this area it particularly was. And here I've got gridded data coming from the Met Office over a grid over a 60-year period. So hopefully what you've seen so far is that if we think about heat waves, there's no natural sort of ordering that you can say this one's an extreme and this one's not, or this one's more extreme than another. There's lots of different ways you can order these because of the spatial temporal characteristics. But natural questions are sort of how often will we get a heat wave? Maybe an exceedance of a high level. How long will those last? So we can sort the duration's important. what area, what's the spatial extent of this heat wave? How will heat waves change with climate? That's not just climate change, but other climate modes that we understand about. And what's the chance of getting a more extreme event than the events we've seen? I'll mostly focus on this latter question for both those two heat waves. So just to try to take out any equations, there's a few equations on the next slide, take out those and just try to give you a strategy of what the modelling is going to be. So let's presume we can compress our problem down just to two variables to start with. So we've got a joint distribution of things with these heat, could be temperatures on consecutive days or something like this. We're going to be interested in maybe in an event like this for this, so we're interested in looking at probabilities of falling in the tail of these variables, where we've got, maybe in this case, both the variables being big. So an extreme value strategy in a multivariate case like this works as follows. We take our data, we pick some threshold above which we view that the observations are somewhat from the tail of a distribution. So we can model using what will turn out to be extreme value models to model the behaviour in that area. We can estimate the rate at which we go above that into the extreme region, just empirically. We've got a large proportion of data either side. We then fit a model to the data up here, and then we use that model, usually through simulation, above at some high level, to derive properties such as the probability falling in a more extreme region. This couldn't be therefore much more extreme than our data. So that's the basic strategy. We've got to pick a high threshold, develop a model, and the model's got to be developed based on sort of the asymptotics of the nature of looking at what we mean by extreme. Okay, so let's now look at this in a multivariate context to understand how we're going to model the dependence. So let's just consider a vector with different margins at the moment, and now everyone's seen copulars, so this is a joint distribution. We can break it down in terms of the marginal distributions and the dependence structure, which is encompassed through this copular function here. So to develop a model for the overall joint distribution, we need models for each of these distributions and one for the copular. So there's obviously infinite number of possibilities here. But because we're going to focus on the extreme regions, we're going to have, extreme value methods will give us insight at least into the tails of these distributions. And the copular, it turns out, once we focus into the extreme regions, although there's an infinite number of possible copulars, we can have a massive reduction in structure once we focus into the extreme regions. A bit like Anthony was finding that once he focused on cluster maxima, he didn't have to look at all joint distributions, he could look specifically at max stable processes. Okay, so first stage is to model the marginal distributions. And then to help us study the dependence, just like Anthony did, we transform the variables onto a standard margin. In my case, I'm going to put them onto Laplace margins rather than Frechet margins. It's a mathematical choice. I could have put them onto Frechet margins. And then look at the copular in that tail region, and because I'm in the tail region, I can simplify its structure down. And in particular, I'm going to end up using a modelling form that comes from work of Jan Heffernan, and there we found that the copula, if we focus in these tail regions, has a particular, very simple mathematical form, and as I say, we then derive properties from simulation from these models. So just stepping through those stages, we model the marginal distributions using the peaks over threshold generalised Pareto type approach for Tenton Davison set out with Richard Smith in the 80s. So we model exceedances over thresholds with a parametric form, which has got an asymptotic justification if the threshold's high enough, and we use an empirical distribution function beneath that. So once we've got our model and fitted that model at each of our variables, we then transform, just using the double use of a probability integral transform to get the variables to have Laplace margins. So now we can focus on modelling new variables, I'll call them x, where each of the variables now is on the same marginal scale, and that makes it easier to describe dependence at least at a visual level. And in particular, we can talk about being big being the same value on the different scales, on the different variables. So when we come to look at extremes, we tend to want to look at the chance of big values occurring together. So the classic measure for looking at this is this value chi, which is the limit of the probability that given one variable is big, that another variable in the vector is also big. And big is now meaning the same thing because they're on the same marginal scale. If that probability in the limit, as the big becomes bigger, is positive, it says that obviously the biggest values of the two variables can occur together, even if we go far, far out into the tails. Whereas if it tends to zero, then they can't occur. The biggest ones in the limit don't occur together. And lots of different models have these different properties. So the max stable models Anthony was talking about can only meet this asymptotic dependence property, whereas, say, if you just start off with a Gaussian process, that would have this property at all levels of correlation. Now, taking things absolutely to the limit isn't what we're really interested in. In practice, we want to model it at observed levels of x and just beyond the data. So we're going to look at this measure for large values of x rather than at the limit, and use that as a diagnostic for our modelling approaches. So this is the scary side, so sorry, I'll give some notation in a second which will make it easier. So let's just pick this off. What I showed in my picture before was I was going to condition on one of my variables being big. So that's what I'm doing here. I'm going to then look at the distribution of that variable given that it was big. And this probability result says that that converges to an exponential variable. That's obvious because I'm in Laplace margin, so it's consequence immediate of that. The subtlety of this comes in this part here, which says that if I take the rest of my variable, leaving out the first one, or the ith one, I can normalise that in some way depending on the one I'm taking out or conditioning on, in a linear way, and then and scaling is in a powered way, and such that this variable, in the end, this joint variable, vector variable, converges to a non-degenerate limit. And the importance thing here is that this is a product, so these two variables in the limit are becoming more and more independent of each other. So we can find some sort of vector values that will do that, and that happens under very weak assumptions. So whichever copula I start off with, I can reduce it down to saying, well, really all I need to know, if I'm looking in mixed extreme region, is I need these vectors of alpha and beta. So let's focus on the bivariate case, because the notation's heavy there. So what this result's saying in the bivariate case is just this: I can sort of relocate and rescale the variable in such a way that I get some interesting distribution to this once the one I'm conditioning on is large. And if these were bivariate max stable, then alpha would be 1 and beta would be 0. In other words, just go back to here, as this one gets big, this one's getting big at the same rate, so the probability of them being big together is greater than 0. So them getting big at the same time means obviously they must be the same size as each other, so the difference between them should converge in nicely to a distribution. But any case where that's not the situation, when alpha's less than 1, we have this asymptotic independence, and this formulation allows us to dig in deeper at what the convergence is there. And in particular, we can tease out special cases of where the variables are positively associated, or where they're independent, so we don't need to normalise x2 at all, or negatively dependent. Now, jumping back to the vector notation version of this again, if we apply this limit and assume it is, as typical in extreme value methods, that this limit holds above some high threshold, then, and then we use that as our basis for modelling, what that really says is that once I look at a high enough level for the variable I condition on, then I can write the rest of the vector into this form. And in particular, this z variable is independent of the variable I'm conditioning on. So it's top of line, you can see it's like a regression setup, but with a single covariate xi, and xi is large. The complication, you can't quite see it's that in that form because this hasn't got zero mean and unit variance. So this is the same thing written with now an error variable which has got zero mean and unit variance. You can now see it's a multivariate regression with a single covariate with a mean function this and a standard deviation function this, so it's changing in xi. So hopefully this picture brings that out in the two-dimensional case, that what we've got is we're modelling how the second variable changes with the first one in its mean value, and in its sort of quantiles are going to change and spread out depending on the values of alpha and beta. So we can use regression then to fit models of that type, very easily get the alphas and betas, and then we can go ahead modelling using an empirical distribution function for the G. So if we go back to this sort of strategy slide I had earlier on, we fit this model above this level. In this case, there's very strong dependence, probably asymptotic dependence, so a straight line with gradient 1 would be fine. We work out the residuals from that distribution. When we model, we can simulate larger values by independently generating a large value on this variable, combining it with the independent residual, get a sample, and then we can count these probabilities. So just a regression situation, the key difference is we've got a particular form for regression behaviour and in terms of the mean and variance, and we're only applying it above a high threshold, not over the whole relationship. Okay, so that's That's the setup that we need. Now we'll just dig into these two case studies to apply this dependence technology to those situations. So looking at the temperatures in central France at just one location, we wanted to fit a Markov model. So we've got to decide what order Markov model to fit. So time series, of course, you look at partial autocorrelation functions to do that. The complication for extremes is that those are based on all the data rather than just on the extremes. So they could have a different structure in the extremes. So as a starting point, I'm just going to take lag 1 dependence, but then we'll come up with methods to look a little bit more detail at the other situation. So we can model now, because it's first order Markov, we only need to worry about modelling pairs of variables. We can estimate our parameters that link the variables together, and then we can easily look at the progression of a chain further on. We've taken a big value, simulate that from our model, and then simulate the successive values using this first order structure. So this shows it diagrammatically. We simulate a value, let's get to the beginning, and then we use this conditional model to simulate forward using the structure of our model, and we can then simulate backwards and we can generate realisations of the event. If we do that, we get that the level that we got at this site was a 50-year level in terms of its peak, so not that particularly extreme. But I'll jump down to here. The probability of this event lasting 11 days was basically a 1 in 1,000-year event. So the feature of this event, which was particularly extreme, was its duration. It lasted an extremely long time. We can also do the same thing with kth order models, and I'll jump through the details of that, but we have now diagnostic methods to identify within the extremes what the order of the process would be, rather than using the classic partial autocorrelation function. But the key thing is looking at sensitivity to the choice of the order. And here you can see that if we look at the probability we get a cluster of at least 11 days, that probability is very small if we look at the first order Markov process, but it increases and then stabilises up by the time we look at a third or fourth order process once we account for sampling variation there. And our diagnostics suggest about a third order process is appropriate in this context. Just quickly jumping back to the Australia study, we're going to apply these multivariate methods to the gridded data from Australia. I'm just going to look purely in space, what's happening, ignoring time, a bit like Anthony's just done. I'm particularly interested in the effect of the ENSO covariate. So this is the El Nino Southern Oscillation, which is known to affect the climate in Australia. I'll jump past that. Right, so first of all, we want to estimate the effect of El Nino on temperatures. So this is an estimate of 1 year return level over Australia in the year when it was the observed El Nino for 2009. And this map shows some of the changes if we've been in different cycles of the El Nino. So we can see that particularly different stages of the El Nino would have affected temperatures most on the East Coast, which is natural given its structure. We can also look at the clustering effects of the event, so we can see that if this site here was extreme, on average there'd be about 8 other grid boxes extreme at the same time. And we could again look at how the El Nino affects that, and it seems like it has almost a very random pattern there, which is interesting given later results. We can look at whether our asymptotic independence model fits well. So looking at using our chi measure as a basis for this. So this is a chi measure at the 90% level and at the 1 year level. So you can see as we go to higher levels, if we just look at this empirically, we can see that there's lots of clustering of extreme values along that diagonal I mentioned earlier. But given that Melbourne was big, but if we look at higher levels, it becomes much more localised. So the events, as they get more extreme, become more focused. Our asymptotic independence model captures this feature almost exactly, whereas the max stable model fails to do that. It keeps the same level of dependence as we extrapolate further into the tails. I'll finish with showing you a severity area frequency plot. This is a plot to try to summarise spatial fields that comes from drought modelling. The basic idea is to look at a plot of, over J, the J average worst effective return period. So picture an area like this. We pick out the worst return period at a grid box and plot it as position 1. We then pick out the worst 2 return period events from the same event. Those two, average those return periods and plot it at position 2 and so on. Now, if we look at the 2009 event, conditioning on it being exactly the size it was at Melbourne, and then simulate under max stable and asymptotic independence models, the observed is here, which is this line, and it doesn't fit within our asymptotic independent models or the asymptotic dependent models, which is bad. But as soon as we put the effect of the El Nino cycle into here, our asymptotic independent models, on average, capture exactly the behaviour of this event. And we capture that nicely within the variation, whereas asymptotic dependent models don't capture this at all. So I think that hopefully what I've given you is a sense of that within using asymptotic independent models, particularly over these larger spatial scales, and Anthony particularly was working on earlier, they start to describe a dependence there that is there in the extremes, but in particular it fades out and disappears as you look to more and more extreme events, but still is critical in the risk assessment over such fields. Okay, thanks.
Thank you, John. We'll start at the front, so we'll start with David.
So you mentioned about that you were thinking about time lag 1, so one observation and then the next one, and you showed your partial autocorrelation function, suggested you might need to perhaps go beyond that. Did I miss it? Did you talk about ideas for extending to if you can't use the Markov property in that situation?
So we found, okay, you can apply this at any order. And okay, so I didn't show these diagnostics, but there's if you can, when you apply the same multivariate joint distribution, build it up as a conditional, as I was approaching there, if you look at the observed chi over different lags, you see that particularly the yellow here, which applies after lag 3, which is when it's lag 3 dependence, captures that, and that still captures that as you move to much more extreme levels as well, whereas to a first order, you seem to get the decay slightly wrong in these more extreme measures. So you can look at pairwise features under these different Markov assumptions, looking at how they fade out as well. So it develops a tool which extends to extremes. It's the classic partial autocorrelation function.
Other data?
Because you found asymptotic sort of non-independence, I wonder whether a sort of Gaussian copula would work quite well, and then you can use sort of Gaussian processes like a time series methods and things like that.
Well, of course, that's just one of an infinite set of asymptotically independent models, and in particular, if I just go back to the structure here, okay, so if x1 and x2 were actually Gaussian, the structure I'd get is that alpha here would be rho squared, which makes sense, okay, with stronger correlation there. But the complication here is that beta would be equal to a half, and it would always be equal to a half. And so, you've got some restriction into the broader class of what you have. So if you're willing to accept models where I'm always going to fix out, as you extrapolate, how much these spread out at the rate at which they spread out, then go with your Gaussian copula. But if you want the flexibility to say that actually my data might have different structure to that, then you need this broader family. But it isn't that much broader, but it shows that the Gaussian doesn't quite give you everything you need to give you the flexibilities. Particularly if you focus, and of course if you fit the Gaussian copula over all the data, you get information about the dependence parameter from all the data rather than the information that might be in the extremes, which is also
about the extremes,
different.
just about using Gaussian.
Yeah.
Yes, John.
Yeah, I was interested in where you're using covariates in the modelling of the Australian data. Did you include the covariate explicitly in the dependence model?
It comes into the dependence and into the marginal features explicitly. So it's coming into alpha, beta, mu, and sigma into its form. So it sort of plays a role in all of those. It is significant in all of those terms. Yeah.
And can you do some analogue of significance testing?
Sure.
Okay, time for one more quick question. Okay, which I will ask. I noticed you have, with the Australia data at least, you have this gridded setup of the data, and you're doing this multivariate regression here. So can you exploit that gridded structure during the multivariate regression?
Yeah. So I mean, what you're sort of hinting at. In some sense, when I'm building up these models, not necessarily in the marginal, but in the dependence characteristics as well, that try to exploit the fact when I fit these that the neighbouring values will be somewhat similar. We haven't explicitly tried to do that. So, I mean, it's an odd one, isn't it? Because in some senses, this data has already been super smooth because it's gridded data. So how much you want to let the data purely stand for itself at that stage, or you want to risk smoothing it further, is a difficult one. But clearly, that's the type of thing that's done in lots of other areas, yeah, and it would be possible to do it. Yeah.